All right, so I'm not going to be talking about databases, not even about testing. However, stick around. We are going to try to make stuff as efficient as possible. We are going to make stuff more privacy preserving. And we're going to learn about some fancy crypto and protocols that you can use right now. OK, so hi, I'm Frank. I work for a company called Fastly. They make internet fast. Check them out. I like open source, and you can find me on social networks. Cool. Let's talk a little bit about authentication. Why is it that we are allowed to stay in this building right now and that we don't get kicked out by security? Yeah, well, before the QR code, we have just a piece of paper. And actually, the security folks don't care about who you are, what you do. All they care about is the fact that you have a piece of paper that's black, because there's some kind of convention that for this conference, people are supposed to have a piece of paper that's black. And prior to that, we had to scan a QR code, which happens to just be a 5-digit number, which is a timestamp. So I'm not going to comment on the security level of the scheme. But these are two examples of authentication. So here's an informal definition of what authentication is. We have 3 components. The first one is a statement. I'm allowed to be in this building right now. The second one is a proof. I have a piece of paper that's black with white text on it. And a verification system. The fact that some people know that they have to check for the color of the badge to see if you're legit or not. So 3 components that work together. In order to actually be useful, well, it would be impossible for someone to forge a valid proof for an arbitrary statement. Or if we already have a proof, it would be impossible to forge a different statement that will verify with this proof. Well, in this case, I'm not sure that this holds true. But we're going to try to do better. OK, so why do we need authentication in distributed systems? Well, there are many, many reasons why we need authentication. Access control is probably the most obvious one. Rate limiting, observability, tamper resistance. This is especially true if you store things on third-party cloud providers, for example. And there's more. OK. So I'm not going to be focused on how to authenticate users, but rather how different services can talk together in a secure way. So one thing we can do is use maybe MTLS. So the way regular TLS works is that prior to setting up a secure tunnel, there is a handshake. And during this handshake, the server sends a bunch of certificates that the client can verify in order to verify that it's talking to the right server. OK, in MTLS, this is exactly the same thing, except that in addition to the server certificate, the client can send its own certificate so that the server can verify that you're legit and eventually who you are and what you're allowed to do later. So that's exactly the same system as regular TLS, but with certificates both ways. OK, so if you can use MTLS, do it. I mean, TLS is fine. It's OK. However, it's a pretty heavyweight solution. Sometimes you may want something a little bit faster. It's transport specific. It works only when you can be in an interactive protocol. And it's a pain in the butt to set up, especially if you need to create new certificate for clients. You need a PKI. Sometimes, if you have a proxy or a CDN, you're not allowed to use custom certificates for the client or to retrieve them, or the library that you are using does not support that. If you're using a web browser, you can actually force the web browser to use client certificates. It's just a terrible UI, and nobody does that. So it might work, but it's not always ideal. there is something else that people use called JOT. So JOT is a format. This is not a protocol. This is just a way to encode a statement and a proof. So this is what a really minimal JOT token looks like. This is base 64 encoded something. And this something is three things, actually. We can only see two, which are JSON objects. So the statement can be just about anything. So you can encode a username, user ID, a picture, whatever you want. Some people use this to secure video segments. So a JOT token can be ginormous, and people actually do that. This is terrible. So if you have something, because we are using JSON, if you have some binary data, you have to base 64 encode it, and then you JSON encode it, and then you base 64 the JSON objects. Of course, why not? OK, back to the previous slide. So we have two JSON objects, and the first one is unprotected, which means that anybody can change anything. And this is going to describe how to authenticate the second block. So the first line, AG, describes the algorithm, which is going to be used to verify the second block. So we serialize everything in base 64. We compute some kind of proof that we serialize using base 64 again, of course. We add some dots. And we get the JOT token. Well, already we can see that it's not super efficient. There's another issue with JOT. This is the living proof that, oh, it's a standard, doesn't mean that it's good. It's absolutely terrible, by design. It's like it's never been reviewed by anybody who knows something about security. Yet everybody's using it because it's a standard. So a famous issue is that because the first part that contains the algorithm can be changed by anyone, you can actually issue a token which is super secure using a completely fine algorithm, and then someone can send a token to the verifier saying, hey, this is what I want. All right, what's the algorithm? None, because you can change it to none, so the verifier is going to be like, OK, cool, it's a valid token. So you can change the algorithm. And this is a massive security issue by design. So if you want to implement JOT, don't read the spec. Just read security advisories instead. Plus, real-world usage and implementations are completely inconsistent with different kind of extensions. And for the same property, you can have different types. It's a mess. JSON doesn't enforce a specific representation. So because you're not guaranteed that some payload will have only a canonical representation, well, you can have two tokens that look completely different but represent the same thing. And for some protocol, that can be quite devastating. Plus, of course, JSON and base 64 encoding is inefficient. But there is more. The verifier can, well, has to accept arbitrary, untrusted JSON data. So hopefully, the implementation that you're using is using a streaming JSON parser and keeps memory usage under control in order to avoid DOS attacks. Of course, all the libraries don't do that. So this is what you can get. There's an improvement. Well, they tried to improve it, which is called CWT. It works exactly the same way, except that instead of JSON, we use CBOR, which is a binary serialization format, which is nice. It's pretty compact. It supports binary data. It's cool. But they fucked up. Because instead of having three different parts, like the metadata and the payload and the signature as different objects, they store everything in a single CBOR object. So once again, you have to use a streaming CBOR parser if you want to avoid DOS attacks. I'm not aware of any implementation that supports that in any language. OK, so what can we do? Well, this is something we can do. So we have some payload. We are going to use whatever we want to encode our data. If it's just a timestamp, like when it's going to expire, just serialize that to a couple bytes. If you have something more complex, use protobuf or whatever you want. anything's going to be more efficient than base 64 plus JSON. Yeah. So go ahead. And then compute this proof, concatenate both, and boom, you get a token which is super efficient and super small. Let's do it. But hey, wait. What can we use for the proof, for example? A hash function? So I guess all of you know what a hash function is. But a cryptographic hash function is often described as a one-way function. It's very efficient to compute. However, given the output, finding a valid input is assumed to be hard or impractical. But wait, if we use that, this is not going to be super useful. Because anybody can do that. An adversary can compute a valid token because the hash function is public. This is pretty sad because hash functions are super fast, widely available. All the languages have them, like SHA-256, SHA-512. You've seen that before. Well, that would be secure if the hash function were secret. Turns out that there is a very simple yet very nice construction called HMAC. HMAC takes a key and any secure hash function you want, and it's going to use that to create a new hash function. For every single key, you're going to get a new hash function. So for a given input, if you have two different keys, you're going to get two completely different outputs. So for an adversary, it's impossible to compute a valid proof without knowing the key. And with newer hash functions, you don't even need HMAC. They support the key by default, and this is more efficient. So same thing, this is something you can find in any programming language, very classic construction. So what can we do? Well, for example, we want to emit a token, which is going to expire. We just encode the expiration date as a couple bytes. We may add a key ID if we want to support key rotation. And then we compute a HMAC over all of this using a secret key. This is super easy to implement. OK. So this is a pretty nice scheme. By the way, you can quite often truncate the timestamp, because if the token is only valid for a couple minutes or hours or days, you don't need to store the year, the month. You can apply a mask to the binary representation of the timestamp in order to save a couple bytes. OK, so this is what the token can look like, a key identifier, a truncated timestamp. And quite often, because the token is going to expire pretty quickly, it's impractical for an adversary to conduct a brute force attack. So how many queries an attacker would be able to do in like 15 minutes or whatever the TTL of your token is? Less than 4 billion, maybe? I mean, if you don't detect this attack, there's something wrong with your system. So in this case, it's also safe to truncate the output of HMAC. So if we combine all this, for the JWT token I showed at the beginning, we can reduce this to only 16 bytes, including the signature. OK. So we used HMAC. That's a very traditional construction. It's cool. And hash function can take arbitrary large inputs in general. However, for authentication, it's very common to have very small payloads. So there are hash functions that are specifically designed for short inputs. So here are some of them. Simpira is a classic. Arion is pretty new, but it's rock solid. You can use it. It relies on AES. It's pretty safe. So why would you do that? Well, that may be why. So you can compare the speed of SHA-256 with Arion. And even a new hash function such as Blex3 is much, much, much slower. But this is only for short inputs. There is a max length that you can hash. Same thing for authentication. You can use the same kind of hash functions with a key. And in this case, this is like 60 times faster than using HMAC. So it's not a micro-optimization anymore. This is really a great speed up. So this is for a payload which is up to 48 bytes. But that's OK most of the time. If you just have a user ID and a timestamp and some simple metadata, that's enough. And it's super fast. But wait, we can do something else. HMAC is based on hash functions, which means that when we have this output, we can't find an input. That's cool. It's a super useful property. However, for authentication, we don't care, because we have the input. So we can weaken the authentication code a little bit and use a secure MAC. So MAC is just an authentication code. So we can use something which is going to be a little bit less secure, but we absolutely don't care in the case of authentication. So there is one way to build a super efficient function that would work in this case, which is to start with a hash function which is super fast, but maybe not secure. For example, maybe it's possible by observing multiple hash and inputs to recover the secret key. But that's OK. All we want from this function is that it's fast, and also that the probability of a collision is very small. After we do that, we can apply a stronger hash function or do encryption. So this is something you can implement using some well-known functions that are implemented everywhere, like ghash or poly 1305. However, there are other constructions that are pretty efficient, especially because they are based on AES, and all the modern CPUs on server, desktop, mobile support AES acceleration. OK, so some of them include Pelican MAC by the designers of AES themselves, Aegis MAC, which is being standardized, STH, which is derived from something used on Android, and Eli MAC. So let's see some benchmarks. So this is supporting arbitrary lengths of any arbitrary inputs of any length. And that's pretty fast. There is a catch for Eli MAC, which is that this speed is achieved using some pre-computation. So you have to define the largest input that you are going to process later, and then store some data. But it's OK. You get a pretty nice speed up just by using this technique. So implementations are available, and it's derived from LightMac, which is not well known, but it's an ISO standard. So anyway, just by using some more efficient functions and by getting rid of JWT and base64 encoding and all this inefficient stuff, we go to something which is like 10 times faster than JWT and smaller. OK, this is great. However, in order to verify a token, we have to do exactly the same computation as to create the proof. So everybody has the same key. The verifier has the secret key, so the verifier would be able to create arbitrary proofs for whatever they want. That's not cool. Because, for example, if an employee makes a backup of the company's database before they leave, well, they can pretend to be any customer later. And this is not great. So there are different ways to fix that. One of them is to use hash chains. Yes, I'm not going to be talking about public key cryptography right now, because hash functions are great. So there's a pretty old protocol called SKey. And this is how it works. We start with a random seed. So this is what the client is going to do. It's going to pick a random seed. And it's going to recursively hash this seed many times, like 1 million times. This is fast. That's OK. Plus, this is a small input, so it can be really fast. And what the client is going to send to the server is the tail of this chain. So this is h n times. Remember that hash function is a one-way function. So in order to authenticate later, what the client is going to do is send the previous to last value to the server. The server can very efficiently verify that the client is legit just by hashing this input. And if this is matching what the server had stored, this is legit. However, the server has no way to find a pre-image, so a valid input, for something it stored. So if what the server has stored is leaked, there are no security implications whatsoever. And a key is used only once, because after this is done, the client is going to remove the tail of the chain and use the previous value, and so on and so forth, until the head is hit, and then they can use a different protocol to do a new negotiation. So this is pretty fast, pretty simple, and super secure, because if the server leaks the keys, that's OK. There's no way to reverse the operation. However, that doesn't work well in distributed systems, because you need some really strong consistencies. The client needs to be synchronized with the server. That's not great. However, there is an improvement called T-key, and U-key is some kind of abstraction over S-key and T-key with also a suggestion to improve the security of the scheme. So it works pretty much the same way. We start with a seed. We recursively hash many, many, many times. However, each iteration represents a time window. So when the client wants to authenticate, they're going to pick the value for the current time window, send this to the server. The server is going to run a couple iterations of the hash function until it gets a match with what was previously stored. And that's it. So we get something that can be reused. We get something that works way, way, way better in distributed systems. Eventual consistency is fine. Even clock skew is fine, because the server doesn't have to always store the latest value they get from the client. You can have some wiggle room in order to accommodate for clock skew. So this is a pretty nice scheme. So you may be like, OK, so the client has to recompute the hashes every time. Well, you can do that. You can do it, but this is not efficient. So an obvious way to fix it is when you create the chain the first time, you store some pebbles around the route so that you can restart, but not from the beginning every time. OK, so very simple scheme. It's pretty secure, pretty fast. However, it still requires states. What can we do to avoid states? Well, traditional thing is to use public key signatures. So a public key signature system has 3 components, or 3 functions. The first one is going to create a key pair, because instead of having just one shared key as we had before, now there is a key to create a proof or a signature, and a different key to verify a signature. So if the verifier only has the public key, there's no way to create a valid proof. The secret key is required. So if the public key is leaked, that's OK. It doesn't have any implications. So we have a keygen function, a signature function that takes the secret key and some arbitrary data and returns a fixed-length signature, and a verification function that takes the public key, the data, and the signature, and returns yes or no. OK. Well, you may be like, well, this is crypto. It must be complicated and dangerous to use. Well, let's see what it takes in practice to do that. Let's do it in Go, for example. Well, it's exactly like the previous slide. This is all it takes. So this is super simple. There are a bunch of algorithms that you can use that works exactly the same way, and they are completely safe to use. So create a key pair, sign, verify. So don't be afraid to do it. Crypto is dangerous, but this kind of thing, that's super simple and safe. OK. Now, we're going to take a look at signatures from a different perspective. Like on an iPhone, if you take a look at the Apple Store, apps are signed both by the developers' secret keys and by Apple. There are two signatures. And these signatures have a completely different meaning. The one from the developer is about identity. This is who made this app. The second one, made by Apple, means something different. It means that before being available, this app went through static analysis, maybe some manual review. It doesn't use undocumented APIs. It's telling something. Just the fact that a signature that verifies under a specific public key verifies conveys some meaning. So we can assign different meanings to different public keys. And it turns out that signatures are pretty small, like 55 bytes max. It's OK. It's not too big. So it's perfectly fine to have multiple signatures for the same payload. And if we do that, it's very easy to add signatures, remove them. So we can attach some kind of metadata to the payload. And this metadata is not arbitrary. There is someone who actually knows the secret key that is responsible for each signature. So let's see one use case for this. We have a client, we have a server, and what we want to enforce is that all the calls from the client to the server go through a gateway. We don't want any ways for the client to directly contact the server. So of course, that can be done at network level, but if we can add some crypto on top of that, even if we screw up on the network, it's going to be safe. So this is how it's going to work. The client is going to take the payload, send it to the gateway, but prior to doing that, it's going to add its own signature. The gateway is going to add its own signature as well, and the server can verify that both signatures are present. If this is not the case, something fishy is going on, I can drop this packet. We can do something else, because in this case, we don't preserve the order. The gateway can be signing the packet first, and then the client. Maybe we don't care. But if we do care, it's perfectly fine to sign a signature. So the client is going to send the payload to the gateway with its own signature, and the gateway is going to sign the signature of the client. Now, there is no way to change the sequence. The server knows that it went from the client to the gateway and from the gateway to the server. So we can enforce a specific path. So that applies to authentication as in access control, but that can work for anything. For example, if you're deploying WebAssembly files or whatever, well, before running the WebAssembly code, you can verify that it contains signatures from the development team and CI and the security team, and maybe each signature represents a specific capability or privilege. So different signatures can be attached to this, and you can have different behaviors according to what signatures are present or not. Something else that could be done is blind verification. So in this case, the gateway doesn't have access to, well, what we want to do is that the client is going to send something to the server, but we don't want the gateway to know what that is. However, the gateway can still see the signature. So one way to do it is to encrypt the payload. We are going to encrypt this payload for the server. The gateway doesn't know the secret key. So all the gateway is going to see is something that looks like gibberish plus a signature. Just like before, the gateway is going to add its own signature, and then the server will be able to verify that both signatures are present and decrypt the payload. Another way to do it is that the client can send the payload directly to the server, and at the same time, it's going to send a hash of the payload to the gateway. So just with the hash, the gateway has no ways to know what the actual payload is. The gateway is going to sign this hash, send it back to the server, and same thing as before. So Why would we want to do that? Well, because the gateway is still seeing the signatures, even if it doesn't know what the payload is. But the gateway can do logging, telemetry, rate limiting, alerting, monitoring, etc. Because maybe one of the signature, given the public key, means that this is a breaking change. So the gateway can log this, or maybe raise an alert on Slack, or whatever. So it can do all these things without having access to the actual code. Because maybe the code is sensitive. Maybe it's running in a secure enclave, or whatever. OK, just a little something on the BBS signature scheme. So you may be like, all right, that's cool. We can attach many signatures to a payload. That's great. But I want to be really hardcore, add 1 billion signatures. This is not going to scale. Yeah, sure. However, if you have many signatures, there are aggregate signature schemes that allow a very compact representation of multiple signatures, such as the BBS signature scheme. However, BBS does something else. It's possible, given a payload and a signature, to compute a valid signature for a subset of the payload without having access to the secret key. So why would we want to do that? Well, imagine that A is calling a service on B using a token. And in order to run this service, B needs to communicate with C. But instead of sending the original token, B can remove the information that C doesn't need and compute a valid signature for that. Maybe because this is just sensitive information or not useful, and B doesn't have access to the secret key. That's fine. So this is a very powerful system. So BBS is not the only algorithm supporting this. However, this is something that's being standardized right now. So there is a draft. There's going to be an RFC soon. And the W3C is also working on this in the context of a different effort, which is verifiable credentials. So this is something you can use right now because it's going to be standard and there are implementations already. So pretty cool stuff. However, it's not that fast, but it's cool. OK, let's talk about RSA. So you're probably like, well, RSA is something old. Nobody should be using that anymore. It's dangerous. It's terrible. Well, in theory, RSA is absolutely fine. But it has to be implemented correctly without side channels, which is not always easy. You need to use it with correct parameters. But the good news is that many protocols built on top of RSA enforce safe parameters. So you don't have the choice. You have to use this set of parameters. So it's a little bit safer to use. So RSA is still fine today. And it has a nice property, which is that verification is very fast. Yes, faster than ECDSA and EDDSA. So if your use case is doing a lot of verification and you don't care about the fact that RSA keys and signatures are very large, use RSA. It's fine. Some mods are a little bit dangerous and hard to implement correctly. Other mods are completely fine. But it's also a great building block for fancy things. Let's talk about them. So let's imagine that a customer buys access to an API. So they get a token to use this API. Well, when we issue this token, we can store information about the customer, like even credit card information or whatever we want. We can even encode some information in the token if we want to. So later, when the token is used, it's possible to recover the identity of the customer. Both are completely linked. Issuance and usage are linked. Well, usually this is OK. But what if, for example, this token is used to grant access to a VPN service? This might not be great from a privacy perspective. Because when the token is used, you can see all the traffic from this person, and you know who this person is. Not cool. Ideally, we'd want to disconnect issuance and usage of tokens. Is there a way to do that? Introducing blind signature. Okay, disclaimer, I'm a co-author of this specification. So this is how it works. The client is going to create a random message. We don't care about the content. We only care about signatures. And it's going to hide it with some secret factor. The server is going to receive the blind message and sign it. So the server signs something which is not the original content. However, because RSA is not too bad, there is a way from this blind message and signature to compute a valid signature for the original message, if you know what the secret factor is. So this is exactly what the client is going to do. And the client is going to end up with a message and a signature, which are completely valid for the public key of the server. But the server signed something, but doesn't know that it's actually matching the token that it's going to receive later. So if you have an Apple device, this is probably something you're using right now. This is used in private relay, for example. It was used in the Google One VPN. Since this is a Google product, of course, it was, it was discontinued. The privacy path protocol, which is used for rate limiting, and some other new protocols. So once again, the actual message doesn't matter. What really matters for verification, so to be able to say, hey, okay, this is a valid customer, is the fact that the signature verifies under a given public key. This is an anonymous ticket. Okay, well, do we have a bit of time? Maybe we do. Okay, so I'm going to talk about a spicy subject. Key distribution. So generally, just like revocation, we don't talk about that. We assume that this is a protocol issue. Cryptographers don't deal with that. But still, so PKI is a partial solution. If you want to deploy a PKI, you can. It works. This is a single point of failure. So if the PKI doesn't work, your entire system is going to be down. This is not great. But yeah, at scale, this is pretty much the only solution. But in practice, static keys are not too bad. No, really, especially if this is just to authenticate internal services, that's OK. Just don't put the secret keys on GitHub. That would be a great idea. So secret store mechanisms exist. Bitwarden has a great one. Actually called Vault in physical. So you can use the systems if you want to, or even hard code them, or whatever you want. Just don't publish them on GitHub. But it's OK. However, a key shouldn't be used forever, if only because some algorithms may have limits, usage limits. But for authentication, this is not really true most of the time. This is mostly for encryption that you have to be careful. But the question that you have to ask yourselves is, what would be the implication of a leaked key? If a key is leaked today, is it OK if you only rotate the key in 2 years? Depends. Maybe it's more of a legal issue than a technical issue. But this is how you should define the frequency of the rotation. Like, how long would it take to be used by an adversary? Maybe they need to compromise a different system to actually make use of this key. So you have some time. So yeah, so far I've been like, OK, this is super cool. Just build your own crypto. Don't use anything standardized. Well, this is absolutely not true. First, because everything I've been talking about so far is either already standardized or on the standard track, or it's some well-studied construction. So everything can be used right now. And it's often more efficient to build your own custom protocol. However, if you really want to use a standard, there is something which is called verifiable credentials by the W3C. which is a way to publish statements about mostly people. So one of their use cases is like in order to verify that someone has a driving license, the DMV can publish signed statement that anybody can verify. So that's the idea, some kind of standard way to publish stuff and retrieve stuff. The document is pretty large. It's nice, but it's complex. It's very extensive. But if you really want to use something standard, that's cool. OK, just to recap about what kind of authentication system can be useful in which cases. So some of them work online, some offline, some are big, some are small, some are fast, some can offer unlinkability, some not. So it's always about trade-offs. Of course, there is no single scheme that has just plus everywhere. That would be cool, but no. All right, and to finish, if you scan this, you're going to see a gist with all the links to everything I've been talking so far.